All right, so we talked about intermolecular forces and dipoles as being kind of the fundamental idea of this week. And so this video is going to be focused on ranking dipole interactions. So when do we have weak dipole interactions? When do we have strong dipole interactions? And of course, we already know that that has applications in what phase of matter we're talking about, solids, liquids, gases. And then we'll move on in the next videos and we'll start to apply these to other to applications in chemistry. So I guess we'll just get right to it. I'm just going to flip this over to the PowerPoint slides. There are three types of dipole interactions that we're going to worry about. The first one is dispersion forces. The second is dipole-dipole interactions. That's kind of it's the main idea there. And then the third one is hydrogen bonding. So these are ranked in order from weakest to strongest. The weakest is dispersion forces. The next is dipole-dipoles. And then the third is hydrogen bonding. So we're going to start with hydrogen bonding though, because we've actually already seen an example of that. Hydrogen bonding is when we create incredibly strong dipoles, and they are always going to be based on a bond to hydrogen, right? Thus hydrogen bonding. So the bond to hydrogen connected to an electronegative element. So oxygen, nitrogen, fluorine. These are the three main examples of hydrogen bonding. When we attach hydrogen to an electronegative element like oxygen, nitrogen, or fluorine, we create very strong dipoles. We create incredibly strong intermolecular forces, right? And so these are the strongest of these three types. This is what I just said, right? Hydrogen is not electronegative. Oxygen, nitrogen, fluorine are electronegative, and so we get a very strong delta minus on the electronegative side and a delta plus on the hydrogen side. And then we can imagine, right, these lining up where the positives are attracted to the negatives, etc., when we have more than one molecule of these things around. Okay, so hydrogen bonding is very much just you have strong dipoles, they orient themselves such that the negatives are attracted to the positives, and so on, and then positives attracted to negatives as well. Dipole-dipole interactions are kind of the same thing as hydrogen bonding. We're going to have dipoles, right? So we're going to have the uneven sharing of electrons. We're going to have delta pluses, delta minuses. They're going to attract each other in the same ways. The only difference here is that instead of having very non-electronegative elements and very electronegative elements attached to each other, we're going to have elements that are closer in electronegativity, right? So carbon and oxygen are not that far apart from each other, right? Carbon is atomic number of 6, oxygen has an atomic number of 8. Their electronegativities are different, but they are closer to each other than, for instance, oxygen, hydrogen, or fluorine and hydrogen. Okay, so we're still going to see the dipoles in a CO carbon-oxygen single bond, right? The electrons in this bond will not just be shared exactly in the middle. They will be pulled toward the more electronegative element. So the oxygen will have a negative charge. The oxygen will have a negative charge. The carbon, of course, who doesn't have, those electrons are moving away from it, will have a partial positive, and these two things will overlap each other this way. So really the difference between hydrogen bonding and dipole-dipole interactions is a difference of degree, right? Dipole-dipole interactions can be strong, but they're never going to be as strong as hydrogen bonding. So hydrogen bonding is kind of a special case of these dipole-dipole interactions when we have hydrogen attached to one of these three elements. But overall, it's the same idea, right? Negatives line up with positives, positives line up with negatives. Attractive forces are good. They tend to hold things together and create slower molecules, more sticky molecules. Dispersion forces are the weakest, and dispersion forces happen when there are no permanent dipoles present, right? So if you don't have this difference of electronegativity that we have in CO bonds or NH bonds, right? When that's not present, then we get dispersion forces. Dispersion forces are a little bit harder to explain, so they get their own slide, which we'll go to now. So here's an example where we have two molecules of nitrogen gas, N2, that don't have any permanent dipoles, right? There is no difference in electronegativity between nitrogen and nitrogen, because of course, nitrogen is the same thing as nitrogen. But what happens is that these electrons that are in this triple bond, so there's 6 electrons, 2 in each of these bonds, right? Those electrons are not static. They don't just sit there. They do move around. And so occasionally, just kind of by random chance, there will be more electrons closer to this nitrogen than there are to this nitrogen, right? And this is just This is not a permanent thing because each nitrogen is pulling on those electrons equally because they're equally electronegative. And so as soon as there's too much electrons on one side or the other, it's going to pull back and restabilize itself. But for that brief instant in time, there's a temporary dipole. There's just a little bit more electron density on this nitrogen as compared to that one. Right? And so the movement of the electrons in the bond create these temporary dipoles. Right? And they're very small. I've tried to draw my delta minus smaller than usual, my delta plus smaller than usual. They're very small, they're very temporary. These types of forces are very weak. Right? And of course, what happens is that when you have a delta minus here, what's going to happen is this nitrogen is going to try to become delta plus in order to attract that negative charge. And this nitrogen will try to become delta minus. It'll pull a little bit of electrons toward itself to attract this delta plus. Right? And this only lasts as long as this temporary dipole. So as soon as the electrons re-equilibrate and become more equally shared, these dispersion forces go away. So they're temporary and they're weak. But the more atoms we have in a molecule, these things start to add up. Right? And so the example that we always use is if you think of methane. So methane is CH4. Right? Methane is CH4, and methane is always a gas, or at room temperature and pressure, methane is a gas, right? So there's not a whole lot of molecular weight there. There aren't any really polar bonds. There's no dipoles in methane. See, carbon and hydrogen have pretty similar electronegativities, right? And so methane has no dipoles. It has no permanent dipoles, and so it only has dispersion forces, and so it's very, very weak forces. Methane is a gas, right? Those molecules don't interact with each other, they just bounce off each other and keep going. As you increase the number of carbons and hydrogens, right, you can keep going. So butane, you've seen butane in like lighters and those kinds of things, right? Butane is a liquid, but it's very easy to evaporate butane, right? So liquid very easily becomes a gas. And this is an example of increasing dispersion forces. Butane is nothing but carbon and hydrogen as well, but butane has 4 carbons and 10 hydrogens. And so the more carbons and hydrogens you have, the more of these dispersion forces you get, and it starts to add up to a measurable effect. Right now we're into liquids. If you go to octane, which is 8 carbons and 18 hydrogens, right, we've increased the number of atoms. We've increased the number of these temporary dipoles. We've increased the number of covalent bonds. We've increased the number of these temporary dipoles, and we start to see more and more effects. So octane is, of course, a liquid at room temperature that's not terribly volatile, right? It doesn't evaporate incredibly quickly. Oh, it's still not the strongest thing. So, but dispersion forces are this kind of thing, right? They are the force that exists. Okay, let me switch this back over. They are the force that exists when there are no dipoles present, right? And so even molecules that don't have dipoles still have intermolecular forces, but they're not as strong, right? So if we rank these, I want to go over the ranking one more time. The strongest is going to be hydrogen bonding. Hydrogen attached to electronegative elements like oxygens, nitrogens, or fluorine, right? Those hydrogen bonds are going to be the strongest intermolecular forces and all of that, right? Dipole-dipole interactions are next. Those are kind of the less intense dipoles that we see, and then dispersion forces are going to be the weakest. So if you have no bonds that are unequally shared, they have no dipoles in your molecule, then you're looking at dispersion forces, and you're not going to have very strong interactions between them. Okay, so that's dipoles. We've done intermolecular forces, we've talked about dipoles, we have an idea of what makes a strong dipole and what makes a weak dipole and all of that. Where we're going next is we're going to start applying this. We're going to apply this to 2 different problems. The first one is phase changes, so the next video will be about phase changes, going from liquid to gas, gas back to liquid, and then liquid to solid, and solid to liquid, whatever, right? As we interact between these phase changes, we want to talk about what's happening to those intermolecular forces in there, how do intermolecular forces play into those phase changes, all that good stuff. And then the thing we're going to go from there, we're going to go into solutions. So what happens when we mix 2 different chemicals together, 2 different chemical compounds, and what kinds of intermolecular forces do we see when we add in not just the interactions of the molecules themselves, but also those interactions of those molecules with something else, right? And so intermolecular forces are going to play a huge role in that as well. All right, so stick around for those. I hope you get to see them soon, and I'll see you then. Thanks.